if the mean and standard deviation is same for over the time. Now here you see that after differencing this random walk with drift model, this is the differencing. That means yt minus 1 is only a0, at. Now expectations of this means the mean value. This mean value is only a0 since expectations of it is equal to 0. So expectations of mean value, this is constant, this is a0 is a constant. So it becomes stationary and the variance is also constant. So after differencing, I can get a non-stationary series. I convert it into a stationary series. In general, the first difference of a unit root process is stationary. If a series has two unit root, it could be shown that the second difference is stationary. In general, the dth difference process, dth unit root is stationary. Suppose in the first, the series could be like this, that in the first difference, after the first difference, the series becomes stationary. But in the series may be so that that the first difference, after first difference, the series has again some non-stationary characteristics, so it is not stationary. Then if I make another difference, if I take another difference, then maybe the series may be stationary. So so differencing is a tool by which I can make the series stationary, and this is the d unit root, the general dth difference the process with the d unit root stationary. D unit roots is stationary. If there is d unit roots, d number of unit roots, then after dth stationary, the series could be stationary. Now, this is the case of detrending. Here also, the detrending, after detrending, the series could be stationary, as I told you earlier also. In particular, classical OLS inference is valid for the trend stationary process. So, trend stationary, after making the series stationary after detrending, we call it trend stationary. So there is two things. One is the difference stationary, another is trend stationary. Trend stationary series can be transformed into stationary series by removing the deterministic trend. Difference stationary series, that is the unit root, can be transformed into stationary by differencing. Superficially, the deterministic trends look similar to the random walk drift, but there is some difference in the random walk. This is the random walk with drift, and this is the deterministic time trend. To describe the quality of non-stationary of a series, stochastic means inexplicable change in direction, often found in economic process, sometime in climate, where I cannot explain the process of change. Some random walk process like this, but deterministic trend which I can change, plausible physical explanations for the trend or seasonal or cyclical like this. So, we can use the regression model when I can explain the cause behind the change in the values. Now, this is the stochastic and this is the deterministic trend. There are some fluctuations, but this is deterministic because there is a change, particular value. We know that value A0 or something like this. So I know it is a deterministic change. But in the stochastic change, stochastic time series, pure stochastic time series, I cannot predict the value of the future time point. Now, there is a problem of non-stationary time series. Why do we care for non-stationary? As I told you that if the series is non-stationary, it is difficult to use some common tools of econometrics for the analysis of the variables or analysis of relationship of variables like this. Now, most of the time series model only work if the data are stationary, which is called stationary time series model. So, first step in an analysis to check for the evidence of the trend or seasonality. Depending on the type of trend or seasonality, we can remove non-stationary in different ways. Simple differencing, subtract trend seasonal component from the original series. Either differencing or the detrending, I can make it stationary. The regression can model trend or seasonal component. Regression can model trend or seasonal component. Why? There is some problem with non-stationary data. Non-stationary data, we have to remove the non-stationarity in different ways, either detrending method or differencing method. Now there are some informal methods. There is a autocorrelation functions. As I told you, the autocorrelation functions is like this, where k is the lag value. And why we call autocorrelation? Autocorrelation simply in correlation, we generally use two values, x and y. There is two different variables, x and y. So this is simple correlations. But here we say the autocorrelations or autocovariances, anything. Why you call auto? Because the variable is same, variable is y, but the difference is the time. The time point are different. One is t and another is t plus k. So there is different, or t minus k, anyone maybe. So there is only difference in time point, but the variable is same. Variable is y. So that's why it is called autocorrelations or autocovariance like this, auto. So here, this is the autocorrelation functions. Autocorrelation functions is defined by like this. So functions, the natural estimate of rho k is equal to, I estimate rho k or gamma k, and I estimate the gamma 0 for all k, and I get the correlations for k. K means lag. K means not time point, but the lag. Get my point? So suppose I have time points, some time points, say say 1960 to 2000. Now, from 1970 to 2000, I have some data, and say 1970 minus, say, 5 years. K is 5, say. So I have 1965 and onwards. So for each time point, if I place that value from 1965, from 65 to 2000, if I place this value in corresponding to 70, so for 1970, my corresponding value will be 1965. For 1971, my corresponding value will be 1966. For 1972, my corresponding value will be 1967, like this. So I have two series then. One is from 1970 onwards, and another is the corresponding value of 1970 will be 1965 and onwards. So I have two series. Now, if these two series, when I take the correlations between these two series, this is called the autocorrelations with lag 5. Here, the lag, when that means the value of K is 5. So there are two series, and if I take the correlations value of these two series, that is called the autocorrelation, and the process is called the autocorrelation function. Now, these autocorrelation functions, as I defined here, is like this. Now, I can estimate these values, and I can take the correlation values. I can get the correlation values for each K. Suppose I take 5, then I can take value 6, then I can take value 7, which are actually lag values. 5 years lag, 6 years lag, 7 years lag, like this. So, but for each corresponding to each values, I have a lag value, and I take the correlations value. So these are the estimate value, that covariance and variance. I take the covariance and variance of these values, and from those estimated covariance and variance, I can get the estimated value of correlations. So from these correlation value, the pattern of these correlation values over the lag period, I can have the idea about the stationarity of the series. Now, what will be the value of K? Now, there is a thumb rule, because if the K is very large, then you can understand, if the K is very large, then the time point will be very small. Time point will be reducing as we increase the value of K, the time point will become small. Now, how small I can take? There is a thumb rule only. I cannot take very large K for a limited time points. I have to find out some reasonable amount of K where I can get some values, so that I can get a good coefficients of R or correlation. One thumb rule is that K should be greater than T by 3. Oh, one rule of thumb is not to evaluate rho for K greater than T by 3. You should not take a value K greater than total T, means total time point, by 3. This is the thumb rule. So that depends actually. Now, if we plot these values of correlations against the lag value, then it is called correlogram. Now, from this correlogram, I can have the idea about the stationarity of the series. Say this is one series. This series, this is a particular time series. Now this series is almost stationary series because this mean is here, say mean is here is 0, and the variance is almost constant, however not fully constant, but constant. There is some differences is there, but mean is constant. Now, then the value is like this. This bar is actually give the correlation value. So for the if there is no lag, then these 2 time points is same. So for the 0 there should be 1, but if there is a lag, then the values will be not equal to 1, but close to 1. So here it is say 0.6 or something like this. But when the lag, this is the lag, these are the lag. The horizontal axis gives the lag value. Now this lag value, this is the 5 lag, this is 10 lag, this is 15 lag. Now you see this, there is a drastic fall in the correlation value. When I increase the lag, then there is a drastic fall. That means that there is the memory is very short. The memory is very short. That means the present time point, the value of present time point does not have any relations with very past values, with say 5 years past value or 6 year past values. So there is no correlations between these two values. So for a stationary time series, these values change abruptly. This correlation changes or fall abruptly if it is a stationary series. But if it is a non-stationary series, then the decay is very slow. Decay of the correlations will be very slow, like this. Say this is a non-stationary series. Since you see there is an increasing trend. So if there is a trend, I can say that this is a non-stationary series. So in a non-stationary series, the decay is very slow. So while in a stationary series, there is an abrupt change and abrupt fall in the correlation values. So we call it correlogram. This pattern gives the idea of stationarity of this series. So if I have the correlogram like this, I can say this is a stationary, almost stationary series. And if my correlogram looks like this, I can say that it is a non-stationary series. Since there is a trend, that means the mean is not constant. So I can say that this is non-stationary. And for a non-stationary series, the correlogram looks like this. Decay is very slow. That means that, say, in lag 15, that means 15 years ago, the past 15 years value is highly correlated with the present value. So that's why it is a non-stationary series. For the time series containing a periodic components like seasonality, the sample correlation functions exhibit the behavior of the same periodicity. As you see, like here also there is a pattern of periodicity, and here you see the correlogram has also some pattern of periodicity. Now the regression model with non-stationary series. Actually, there is a problem of non-stationarity with the standard regression or classical OLS, COLS model. Classical least square model, there is some problem because it uh, it does not satisfy. If there is a non-stationarity, this does not satisfy. It does not satisfy some some conditions of classical regressions model. Now, now the unit truth issue in the standard regression model. Suppose this is the standard regressions model, and this standard, this y and z, say it is independent variables, y is dependent variables, but this y has some pattern like this, and the z is also some pattern like this. Now, these are stochastic series. These are stochastic term or white noise term. It can be shown, and since there is a sum over t, so if the variance of this error term become infiniteless as t increases, and the error has a permanent component that is mean of error is not zero. The mean of the error is not zero, so the mean of this error is not zero. In our standard regression analysis, we always say that the epsilon t, that white noise, this has mean of this error term will be zero. Hence, the assumptions embedded in the usual hypothesis test are violated. We cannot use the classical regression analysis with the non-stationary data, non-stationary series. We call it actually spurious regressions. I may get a regressions, but it could be spurious regressions. A regressions in which we frequently reject the null hypothesis that beta is equal to 0, even in the case that the null hypothesis is correct. So this is the problem of testing of hypothesis with the non-stationary data. When X, Y, and Z and E contain a spurious trend, well as a spurious regressions. So if there is, these are all non-stationary, these two things are non-stationary, Y and Z are non-stationary, they thought. Suppose these are the two series. Now these two series, say dotted line and the bold line, these two continuous lines, these are two series, and from these two series we can have some regressions analysis. We can get some values of beta and alpha and all these things, but these we cannot test the beta and alpha because it does not satisfy the classical regressions conditions of moment conditions, actually classical regressions moment conditions. So I cannot use those non-stationary data, non-stationary series of the data of A, Y, and Z for usual regressions analysis. Now, just a minute. If both X and Y contain spurious regression, then coincidence is much more likely to lead us into error. If both X and Y happen to receive the large positive shock, they may both stay over their mean for a long time. It will appear that Z being above the mean, above its mean predicts Y being above its mean, we need the correction procedure. So if there is actually a shock, this shock actually does not disappear in future. So the values may be above the mean or below the mean. Now, if the value is above the mean, the predicted value of Y also above the mean. So we cannot have the exact result, or we cannot test the result, test this hypothesis, or I can test the hypothesis of our results. Actually, that say beta, hypothesis of beta, generally we use the null hypothesis beta is equal to 0. We cannot reject the null hypothesis here. If we reject the null hypothesis of beta, if we actually if I reject the null hypothesis of beta, it may not be so that the beta is not rejected, but since there is a problem of spurious regressions, so I cannot test our hypothesis of beta and alpha. Now if this is like this, and if we regress delta yt and delta zt against delta zt, neither the experimental nor the error term contain a stochastic trend. The regression satisfy the Gauss-Markov conditions. That means that classical regressions model, the conditions of classical regressions model. If Y and Z both receive the large positive shock, then delta Y and delta T will be both above their means. However, in the next period, the shock will no longer be evident in delta Z and delta Y and delta Z. So delta Y and delta Z revert to the mean. So after differencing, I can have the series stationary, and I can use those values for the classical regressions model. So this is the remedy of the spurious regression model. So first I have to test the series whether there is a non-stationary in the series. If it is a non-stationary series, then I can use the simple regressions with these non-stationary series. In that case, I have to transform the series into stationary by differencing those values, and then we can use that difference values for the purpose of regression model. This is the way I can get remedy from this spurious regression analysis. Now, what is data generating process? Now, okay, I skip that one. Now, Z contains the deterministic trend only. Z contains a stochastic trend only, and both stochastic and deterministic. This is the stochastic trend and this is the deterministic trend. Now, just a minute. Now, suppose this is the difference equations. Now, the random walk hypothesis requires the testable restrictions that alpha 0 and this is equal to 0. If both alpha 0 and alpha 1 is equal to 0, then delta Z is depends only on epsilon t, which is random. So, this, if if the process, if the values of alpha 0 and alpha 1 is 0, then it becomes a random walk. So the testable condition for random walk is that both alpha 0 and alpha 1 is equal to 0. Now, what is the order of integration? Now, the order of integration is if a series is first order, I mean that if the series is stationary after first differencing, the order, the series is stationary, then the then the series is integrated of order 1. That is called I1. Now, in such a way, if the series becomes stationary after the dth differencing, then the order of integrations is D. That means denoted by ID. That means, say, D may be 2. That means after second difference, the series becomes stationary. If the series becomes stationary after second difference, then the value of D will be 2. So it is integrated of order 2. So in this way, and if the series is stationary without any differencing, then it is integrated of order 0 because there is no differencing. So the differencing is 0. So it is, then we call it that stationary with differencing. Without differencing, we call it integrations of order 0. Okay, now I go to these are the non-stationary, some of the non-stationary series. Could be like this. Generally, this type of series is stationary after first differencing. This quadratic type of series, that means 2 unit roots is there, then it becomes stationary after second difference, and it may be more than or difference, or may not be stationary after differencing. Whether it becomes stationary after differencing, that depends on the type of time series. Now, there will be a test whether before, so far as I have told you that the series is whether the series has is stationary or non-stationary. I can check it in different way. The first is that there is some informal way of checking the stationarity, like taking the graph of the series, or covariance values of the covariance with the lag series, autocovariance values, autocorrelations values, or from the autocorrelation functions or the correlogram functions, correlogram diagram. So from those informal tests, I can get an idea whether the series is stationary or not. But there is some formal test which we call the unit root test. So this unit root test is a formal test of of knowing whether the series is stationary or not. Now, this desired test is now this is the, say our Z is our time series. Now this test Z is a function of Zt minus 1, and there is a constant, that intercept term, and there is a trend, and there is a stochastic term. Now, the test is whether rho is equal to 1 against rho less than 1. That means rho is equal to, if rho is equal to 1, that means if I do not think about this, this beta 0 and beta 1 t, if I do not think about this thing, then zt is only, zt is equal to, if I have zt is equal to rho zt minus 1 plus vt, then if rho is equal to 1, then zt minus 1 is equal to vt, which is purely stochastic. So this is a non-stationary series. This will be random walk, and this will be non-stationary series. So, but if we include these things, that intercept term and the train term, then this remain the same. The hypothesis remain the same. Our null hypothesis is rho is equal to 1 against rho less than 1. But for simplicity, we to test the rho is equal to 1 against rho less than 1, we take the difference of this. That means delta y, delta zt is equal to 1 minus rho zt minus 1 plus these things. So zt minus 1 is equal to, sorry, rho minus 1 zt minus 1 plus this. Now this rho minus 1, this is zt, this is delta z. So delta z is equal to rho minus 1 plus this. Now to test rho is equal to 1, to test rho is equal to 1, so if rho is equal to 1, so what will be the coefficient then? The coefficient will be 0. If rho is equal to, if rho is equal to 1, then the coefficient of zt minus 1 will be 0. And if rho not equal to 1, this is not equal to 0. Now, so I can test, instead of rho is equal to 1, we can test the coefficient of zt minus 1 is 0 against one-sided alternative, that is less than 0. So less than 0, that means rho less than 1 or less than 1. If rho less than 1, so it should be less than 0. That means negative. Actually, this is negative. So this is one-sided test. So 0 against negative value or less than 0. So we cannot use our usual T statistics critical value, because Dickey-Fuller asymptotic distributions is skewed. So Dickey-Fuller, now this is the process. Now I can take it, instead of rho, I can make it as a gamma, say. Or beta here. Here it is a beta. Now here yt is equal to beta yt minus 1, delta yt is equal to beta yt minus 1, delta yt is equal to beta 0, beta this. These are the two, the difference between the three regressions concerned presents deterministic elements B0 and B2. For testing if Y is a pure random walk, it is a pure random walk. If beta is equal to 1, if beta is equal to 0, then this part will be 0, the first part will be 0 in this equation, the first part will be 0. So delta yt is equal to epsilon t, so it is a pure random walk. So The first one is for testing Y is a pure random walk. This is for testing a pure random walk. Second, for testing Y for random walk with drift. Now, if beta is equal to 0, then beta 0 plus epsilon t, which is a random walk with drift. Drift means beta. Now, for testing Y0 is a random walk with drift and a deterministic trend, then a drift and a deterministic trend, then we use the third one. So, the primary objective is that for determining the stationary non-stationarity is that whether the beta is 0 or not. The beta is 0 or not. The null hypothesis is 0 and it is less than 0. Less than 0, alternative hypothesis. So, this is the Dickey-Fuller, we called it Dickey and Fuller, the both two persons, the Dickey and Fuller. Since the distributions is something different here, so Dickey and Fuller use some values of critical values of the significance level at different significance level, critical values at different significance level, which is different from the standard t-test values. So, this is the Dickey-Fuller test. Now, there is another test which is called the augmented Dickey-Fuller, where we consider also the delta Z in the right hand side. Here in the right hand side there is no delta Y or delta Z anyway, delta values. But in the augmented Dickey-Fuller there will be some, since here is a delta Z and this will be like this. Dickey-Fuller assume the delta Z uncorrelated. If we are concerned delta Z are serially correlated, we need to augmented Dickey-Fuller test. If we think that the delta Z are serially correlated, then we need the augmented Dickey-Fuller, where we use that Z and delta Z also, delta Z t minus 1, delta Z t minus 2, like this. That depends on the lag. How many lags I will take, t minus 1, t minus 2, like this. Now, we commonly add 1 or 2 lag in the annual data and 4 lag in the quarterly data. This lag, how many lag I will take? The t minus 1 or t minus 2, like this. Now, note that we can test the presence of the unit truth. Now, we call it Dickey-Fuller statistics. As I have shown you that the table, from that table, I can compare my estimated value and the tabulated value of t or z, and from that value I can compare those values, and either we can reject the hypothesis of stationarity or retain the hypothesis of stationarity. Now, these are some process how we can produce that unit truth test. Okay, there is some process, step-by-step process by which I can say this is the total equations, and first we test actually this gamma value, whether this value is 0 or not. If this is 0, then it is these are the unit truth. And if this is 0, not 0, then there is no unit truth, so we will not go further in this analysis. So I can say there is no unit truth, and this is the is in the standard regression model like this, but there is some steps behind this. how we can conclude that whether there is no stationary, or whether there is this stationary series or a non-stationary series, and also the I mean, whether this trend values is significant or not, whether the coefficient, intercept coefficient is significant or not, I can check from these estimates. Now, there is there is some, there is some properties of autoregressive, this is autoregressive process by which there is some properties of autoregressive process by which I can conclude the series as stationary or non-stationary series. And stationarity, there is some stationarity conditions of the ER model. Why ER model? Because it is autoregressive model, because you see here YT and here YT minus 1. So in the regression model standard, if it is Y, it will be Z or something like this, but this here Y is, both is Y, but there is a difference in the time point. So this is called the autoregressive process. So autoregressive 1, because there is one lag model, lag 1. So that's why it is called autoregressive 1. So I may have autoregressive 2 and autoregressive 3 model like this. That depends on the lag values, lag values here. So there is some conditions of the autoregressive and autoregressive process. So if YT is stationary, if the rho is stationary, this rho is equal to 1, then rho less than 1, then the YT is stationary series. Now, in all the cases, in autoregressive models, actually this autoregressive models is similar to that earlier one, where I show you how the rho value actually that depends, it should be less than 1 for a stationary series. Now, there are some conditions of the finite variance. Now I skip these things. Now there is another important thing in time series is the co-integrations. Generally, if the two values are co-integrated, then we can use those series for checking the long-term relationship between them. So macroeconomic variable, these are non-stationary. Many of these are different stationary. So concept of co-integration, it is essentially a time series concept which is concerned with the presence or otherwise a long-term relationship among the series processes for two or more variables based on a given large data set of time series data on the variable. The econometric methodology of the co-integration estimate this co-integrating relationship. It is necessary that the time series process of the individual variable are non-stationary, having the movement of strain. Actually, when we do the co-integrations, it has a non-stationary series and having trend. Now this should be like this. These two there are two series. Now, if these two series, whether they are individually, they are non-stationary, but if we can get some linear combinations of these two series which are stationary, then we call these two series are co-integrated. If they are co-integrated, then we can get a long-run relationship among these two variables. So I think there are so many items or so many things in the time series and stochastic time series analysis. It is very difficult to cover all these things in short. But I think this is what this debate I should conclude here. Thank you.
Thank you so much, sir. Well, I think two of the participants had raised their hand. They were probably Dolly and Archana. Do you have something to ask, Dolly and Archana?
Yes, ma'am. I have a query.
Please do. Please go ahead.
Sir, I want to know if we make two variables stationary at the same order, can we calculate regression between the two variables?
No. You can do with co-integrations.
That so we cannot calculate correlation or yes. Regression.
No, not correlation. Correlations you can do, but yes, for in regressions there is a dependency of a variables on the other one. So yes, there could be a long-run relationship between these two variables or the short-run relationship between these two variables. Now that can be solved only through co-integrating relationship, and after getting the co-integrations, you use the error correction model or vector error correction model, from which you can understand whether there is a long-run relationship between these two variables or the short-run relationship between these two variables. But this is the problem of co-integrations, which I cannot cover in this lecture. Okay.
Okay, sir. Thank you, sir.
Okay.
Thank you so much, sir. Yeah. Thank you. And I think, sir, in your lecture, comprehensive lecture, you have very well summarized, sir, and have made us to learn about the difference between stochastic versus deterministic, as well as the random walk model, the Dickey-Fuller unit test, unit root test, as well as the augmented, which is known as the ADF, sir, unit test. Yes. And I think there are so many things. I think queries may come up later, or maybe the students or the participants have learned properly whatever you have presented through your PPT, sir. Thank you so much for your time, because it's really a privilege for all of us to hear a resource person from ISI Kolkata, sir. And you have been experienced faculty over there, a scientist there, sir, and your immense work really made us feel that we have been really privileged to hear from you, sir. Thank you so much, sir.
Actually, if the topic will be more focused, then it will be easy to communicate through this lecture, because it is a so vast thing. So it is difficult to cover all these subjects.
I know, sir. I know, but then orientation was very much necessary for all of us to actually know these basic things, sir. And I think that the feedback
is the basic, actually.
Yes, sir. Yes, sir. And sir, the feedback which is coming from the student, the participants, really, I think, sir, they have really liked the lecture. They have comprehended it quite successfully. So thank you so much, sir, for your time. And thank you all the participants. You all have been filling the feedback form. Do fill it, because that will give us a ground to actually give you the e-participant certificate.
So, ma'am.
Yes,
okay.
Sir, I have a question. I didn't interrupt Anamika, ma'am, in between. Sir, as the whole lecture was wholesome, as we read different books से इतना सारा knowledge होगा, और आपने एक ही मतलब एक प्लेटफॉर्म पर वाया पीपीटी आपने सारा जो थियोरेटिकल बेस है वो टाइम सीरीज का आपने हमारा वो बनवा दिया है. सर, while performing the augmented Dickey-Fuller test इन स्टैटा वो तीन चीजें पूछता है सर, तो मुझे उनके बारे में पूछना है कि while applying the augmented Dickey-Fuller test, सर सबसे पहले वो मतलब जो टाइम वेरिएबल है उसको चूज कराता है. फिर 3 ऑप्शन आते हैं सर. पहला ऑप्शन रहता है सप्रेस कांस्टेंट टर्म इन रिग्रेशन, second option is include trend term in regression, and third is include drift term in regression. Sir, इनका मतलब kind of meaning और किस situation में क्या include करें?
Basically, when there is a actually the correlation, there is a if you think that there is serial correlations among Z or that particular variable, then you go for the augmented decay Fuller, where you include that delta Z, delta value of delta Z with lag. Okay, so lag you can have 1 lakh, 2 lakh, 3 lakh, that depends. Generally, we take 2 or 3 lakhs maximum.
Okay, sir.
That is the delta Z, values of delta Z, and that only require when you think that there may be some serial correlations among the values of Z. So, but in most of the cases, we start with the augmented decay Fuller. Augmented decay Fuller with lag, that's no problem. But if these Z values, the coefficients of the delta Z are not very significant, then we can reject that one, those values, and I can take only the decay Fuller part, not the augmented decay Fuller. If the coefficients of the delta Z are significant, then we can use that augmented decay Fuller. Otherwise, we cannot. We can take only the simple
decay Fuller test.
Yes.
Okay, sir. Thank you.
Okay, thank you.
Thank you, sir. Thank you, all of you. We'll meet tomorrow again at 3 p.m. Okay, thank you so much. Have a nice day.
Okay, thank you.
Thank you, sir.
Thank you.